So when we ended our last class meeting, we had determined that our circuit was overdamped because alpha was equal to 100 nepers per second and omega naught was equal to 80 radians per second. So now we're going to talk about what to do with that information. So I want to scroll back up to the original circuit because I feel like I did maybe a less than great job of explaining what's going on here. Okay. So our two signals of interest is this inductor current and this resistor voltage. We were keeping track of the capacitor voltage because we have a transient analysis problem with an energy storage element. And we kind of always need to know what those energy storage elements are doing. At the very least, we need to know what's going on with them at t is equal to 0 minus so that we know how to redraw our circuit at t is equal to 0 plus. Okay. So I'm going to use the table that I gave you guys, and we're going to solve for our inductor current, and we're going to try to solve for that resistor voltage based on our circuit analysis, and we're going to run into a little bit of a problem, and this will kind of explain things a little bit better. So let's work on that inductor voltage, okay? So this is step number 5. So step number 1, just to recap, was analyze the circuit at t is equal to 0 minus. Step number 2 was analyze the circuit at t is equal to 0 plus. Step number 3, analyze the circuit at t is equal to infinity. Step 4 was determine what type of response the system had, whether it was overdamped, critically damped, or underdamped. And now we're on step 5, which is actually collecting all of that information and actually figuring out what our voltage or current waveform of interest is going to be. So we're going to deal with the inductor current first, right? So we are going to start by saying that IL of t is equal to A1 e to the S1t plus A2 e to the S2t plus IL at infinity. This comes directly from our table. Okay. So whenever we have a system that has an overdamped response, this is what our inductor current is guaranteed to look like. It is also what our capacitor voltage is guaranteed to look like, okay? So what we're going to wind up doing here, and you'll see this in a moment, is we're going to wind up setting up a system of equations. And our first equation is always going to be either the inductor current or the capacitor voltage. Those are literally the only two options. Everything else will not work, or at least will not work with the table that I have provided. If you wanted to deal with integral-based relationships and all of that kind of stuff, you're more than welcome to do so. But I have been, I believe, kind enough to provide you with a relationship and a derivative-based relationship that I'm not going to make you derive, and that's what we're going to be using here, okay? So before we get too far into the weeds of this, we're going to need to know what S1 and S2 are. So let's go ahead and calculate those things, okay? So S1 is, by definition, negative alpha plus the square root of alpha squared minus omega naught squared. So I'm going to go ahead and put that in my calculator. So negative alpha was 80, if I'm not, nope, 100. So negative 100 plus the square root of 100 squared minus 80 squared. And this comes out to be negative 40. Actually, I was going to say nepers per second, but let's just put it as per second, okay? It's a frequency in as much as it's per second, but other than that, we don't really care. S2 is negative alpha minus the square root of alpha squared minus omega naught squared. So negative 100 minus the square root of 100 squared minus 80 squared. I get negative 160 per second. Okay, so we figured out what S1 and S2 are. We're going to wind up using those in a moment. So if we look at our expression for our inductor current, let's see what happens at t is equal to 0 plus. Okay. So at t is equal to 0 plus, e to the S1t is going to look like the number 1 because e to the 0 is simply 1. So we're going to have a term of A1 plus, well, e to the S2t, where t is equal to 0 plus is also just going to look like 1. So we're going to have A1 plus A2 plus IL at infinity. And now we're going to substitute in numbers for IL at 0 plus and IL at infinity. So let's scroll back up here. So at 0 plus, IL was negative 5 milliamps. So we're going to have negative 5 milliamps is equal to A1 plus A2, and at t is equal to infinity, we found that IL was equal to 4 milliamps. And simply rearranging this guy, we're going to wind up getting a relationship A1 plus A2 is equal to negative 9 milliamps. Everybody okay with this? Okay. Our second equation is going to come from the derivative-based relationship of our first equation, okay? So what do we know that is related to the derivative of the inductor current? The inductor voltage. Well, for us, the inductor voltage is the exact same thing as the capacitor voltage, right? So we could say that V of t, or VL of t, is simply L times the derivative of IL of t. So all I'm going to do here is I'm going to put an L out front, and then I'm going to look at my table, and where it says dy of dt, I'm just going to put that in because I already did the derivative for you guys. So the derivative of an overdamp response looks like S1 A1 e to the S1t plus S2 A2 e to the S2t. At t is equal to 0 plus, this is going to reduce to L times S1 times A1 plus L times S2 times A2. And we are going to, once again, substitute in our numbers. So at t is equal to 0 plus, the voltage drop across our capacitor, which is the same thing as the voltage drop across our inductor because those two elements are in parallel, was simply 0 volts. So from this, we can actually say that S1 A1 plus S2 A2 is equal to 0. I dropped the L here simply because there's a common factor of L across everything, and so I can divide both sides through by L and it not make any difference whatsoever. The only reason I was able to do this was because VL at 0 plus was 0. So I could just as easily put the L here and the L here. It's not going to change literally anything at all, but I'm going to be lazy and put it in my calculator. It's just S1 times A1 plus S2 times A2. So we have one equation right here and another equation right here, both with unknown quantities, A1 and A2. So we're simply going to solve this system, which is what calculators are for, right? So I'm going to put in here a 2x2 system solve. So my coefficient for A1 in my first equation is 1, my coefficient for A2 in my second equation is 1, and my constant term is negative 0.009. In my second equation, my coefficient for A1 is S1, which was negative 40. My coefficient for A2 is S2, which is negative 160. And my constant term is 0. When I solve this system, let me double check that. I get 3 milliamps here, and this looks like, yeah, negative 12 milliamps. That should work. So putting these pieces of information together, what we'll see is that IL of t is equal to negative 12 e to the minus 40t plus 3 e to the minus 160t milliamps. So we're going to verify this in just a moment with LT spice. Let me make sure I got those coefficients right. Yep, negative 40, negative 160. Okay. Now, let's talk about our resistor voltage. Okay. So we know that our resistor voltage is overdamped, so it should also be of the form. I'm going to call this A3 e to the S1t plus A4 e to the S2t plus VR at infinity, which is going to wind up looking like at t is equal to 0 plus A3 plus A4 plus VR at infinity. I'm not going to worry about numbers because this is about to break down anyway. So now we would need a derivative-based relationship. There is not a derivative-based relationship that exists for resistors, right? So it turns out that we can never actually find out what's going on with a resistor directly. We have to use what's going on with either our capacitors or our inductors in order to figure that out. Okay. So if we scroll back up to the top here, we can see that during the transient condition, the voltage drop across our resistor is literally the exact same thing as the voltage drop across our capacitor. So we could, if we were so inclined, set up a system of equations using our capacitor voltage as our first equation and our capacitor current as our second equation, because those are our derivative-based relationships, solve for the capacitor voltage, and then say that that is the exact same thing as the resistor voltage just by simple inspection of our circuit. However, we don't actually need to do that because we already have all of the information in order to determine what our inductor voltage is. And the inductor voltage is the same thing as the capacitor voltage, which is the same thing as the resistor voltage that we're looking for. Okay. So if we wanted to find our inductor voltage, we're literally, sorry, I scrolled too far, just going to go right back to here because L is a known quantity, S1 is a known quantity, A1 is a known quantity. S2 is a known quantity, A2 is a known quantity. So we have all of those pieces of information, right? Sorry, this should be a V. My apologies. So we're going to have L, S1, A1, e to the S1t plus L, S2, P2 e to the S2t. So L was some ridiculous number like 62.5 henries. Yeah. 62.5 henries times S1, which is negative 40 per second, times A1, which was negative 12 milliamps, e to the S1t, plus L 62.5 henries. S2 was negative 60 per second. A2 was 3 milliamps, e to the S2. And I'm just going to put that stuff in my calculator, right? So 62.5 times negative 40 times negative 12 milliamps comes out to be positive 30 volts, e to the minus 40t. 62.5 times negative 160 times positive 3 milliamps comes out to be negative 30 e to the minus 160t volts. And this will be the exact same as the resistor voltage that we were looking for. So I understand completely that this process is new and it is likely confusing. So we're going to wind up working more examples and all of that kind of stuff, which we have a class day dedicated for specifically. But I just want to see whether or not I am right, which I'm an arrogant asshole, so I always assume I am, but it's good to have things verify that. And so to facilitate that, we're actually going to simulate this circuit using LT Spice. We're only going to worry about what's going on during the transient condition. So during the transient condition, I might have to go back to my original circuit because I don't remember it super great. So during the transient condition, our switch is closed. So we're just going to draw this exact circuit with the switch closed. So we're going to start with a current source. Up. So this should have been 9 milliamps, if I'm not mistaken. Then we had 6 kilo ohm resistor. LT Spice and the Zoom window thingy are not going to play well, so I'm going to pre-apologize for that and just move it down here out of the damn way. $6K. Up here is my switch, which is just short. Then I have, I think, my inductor. Then I have my capacitor, smaller. I have another resistor. Let's go ahead and throw some component values in here. 62.5, 2.5 micro. 3K. Over here, I have a voltage source that's 15 volts, positive polarity on bottom. All right, so one thing that I always do, or at least as often as I possibly can, is I'm going to choose ground since LT Spice requires us to have some ground. I'm going to choose ground to be at the negative polarity terminal of my capacitor, right? So that would be this node down here. So I'm putting ground down there, and I'm going to label the positive polarity terminal of my capacitor as node VC. Okay. So the reason why I'm doing that is because I have to put initial conditions on the current flowing through the capacitor and the current flowing through the inductor and the voltage drop across the capacitor, and that's going to make that easy. So in order to do that, I'm going to use this spice directive command, and I'm going to type in .ic. I'm going to say the voltage at node VC is equal to 0, because that's what the voltage for the capacitor was at T is equal to 0, minus, I'm going to press Control M to give myself a new line, and then I'm going to do .ic I. So the current flowing through component L1 was negative 5 milliamps. Is that what we got with our circuit analysis? I believe so. Okay. I'm just going to put this over here out of the way. And now I'm going to run a transient analysis. So I'm going to edit my simulation command. I'm going to leave it on transient analysis. So I need to figure out how long to run this thing. And so what I'm going to do for this particular problem is I'm going to start with kind of a guess. I'm going to base that guess on the smaller of my natural frequencies. So S1 was negative 40 per second. So I'm going to do 1 over 40. So the reciprocal of that eigenvalue is 25 milliseconds. So let's run this for 125 milliseconds, because that should be enough time, I believe, for things to settle down. And we can always go back and adjust things. So I'm going to run this. I'm going to add a second plot plane here. So this top plot plane, I'm going to look at my inductor current. And this bottom plot plane, I'm going to look at the voltage drop across my resistor. All right, so these are the results of my simulation. Now I'm going to put in the results of our analysis, okay? So with the top plot plane selected, I'm going to add a trace, and all I'm going to do is literally type in the mathematical expression that we came up with, which, if I am not mistaken, was negative 12 milliamps. So I'm going to go negative 0.012 times EXP. Our S1 value is negative 40 times time, plus 0.003 times EXP negative 160 times time. And of course, these don't match up. We'll figure that out in a moment. Seems like I just made a simple mistake somewhere, so we'll sort out what that is in just a second. Let's check for our voltage thing here. So add a trace. So this guy should be 30 times EXP negative 40 times time, minus 30 times EXP negative 160 times time. Okay, so let's look at the bottom thing first, okay? So we have our capacitor voltage VC, and then we have this mathematical expression. When I type the mathematical expression in, the curve completely overlapped what was originally there, which seems to mean that I got the voltage part absolutely correct, okay? One thing that I do want to point out here, the scale on the left-hand side is going from 0 to 14 volts. The scale on the right-hand side is also going from 0 to 14. So that's another quick thing that we want to double check just in case our answer looks off, right? So if the curves completely overlap and the scale on the left-hand side and the scale on the right-hand side are identical, then we're good to go. Now, the scale on the left-hand side here goes from negative 5.4 milliamps up to 4.5 milliamps. The scale on the right-hand side over here goes from negative 9 milliamps to positive 0.9 milliamps. I'm going to change this, but I don't think that's going to fix anything. Yeah, still looks appreciably incorrect. So, anybody have any thoughts on what I might have missed? So if we go back here to our expression for IL of t, we have A1 e to the S1t plus A2 e to the S2t plus IL at infinity. What I forgot, and this is a very, very common mistake, was to add the IL at infinity part, right? So at t is equal to infinity, our inductor current was positive 4 milliamps. So all I really need to do is just tack on a plus 4 milliamps here. And a plus 0.04 here. That's 40, there we go. And I'll be damned, they perfectly match. So just one simple mistake, and it looks aggressively incorrect. Now that we fix that, our analytical solution perfectly matches that of the simulation, which means we did everything right. So we can use LT Spice as a tool to figure out A, whether or not we did anything correctly, and if we did do things correctly, or if we didn't do things correctly, we can also use it to figure out where our mistake was, right? That's why I typically ask you guys for two different quantities. So if both of them look wrong, then there's a big problem somewhere in the analytical work that you did. If one of them looks right and one of them looks wrong, then it helps us sort out where we made our mistake. So anyway. All right, so that was an example of a parallel RLC circuit. So now we are going to look at what goes on with series RLC circuits. And we're going to do this relatively quickly because it's so similar to how parallel RLC circuits work. All right. So let's say that I have the following circuit. I have some voltage source. Here's a switch that's going to open at t is equal to 0. And then here's some resistance, some inductance. Let me put that on the inside. and some capacitance like so. And I am going to say, did voltages in blue. So this is going to be the voltage drop across my inductor. This will be the voltage drop across my capacitor. And this will be the voltage drop across my resistor. I chose to put the positive polarity terminal on bottom because, as we'll see in just a moment, if this is my current I of t that's common to all three of those series elements, now I of t is flowing into the positive polarity terminal of all three of those circuit elements during the transient condition, right? So it may seem like an odd choice to put the polarity of the voltage, excuse me, the polarity of the resistor voltage on bottom, but it was very intentional. All right. So in this circuit, we're just going to talk about things here, not really draw stuff out too much. When t is less than 0, our switch is assumed to have been closed for a very, very long time. Okay. So we have a DC steady state circuit where our inductor is going to look like a short and our capacitor is going to look like an open circuit. So what we should see here is that no current is flowing through our inductor prior to t is equal to 0. So there's no energy stored in our inductor, but there will be some voltage drop across our capacitor, which will just be Vs. So our capacitor has some amount of stored energy, none of the other elements storing energy. Once our switch opens up, then our capacitor is going to transfer its energy to some combination of the resistor and the inductor, and we're going to have a similar situation like we had with our parallel RLC circuit, but now it's the capacitor that's doing everything as opposed to the inductor that's doing everything. Okay. So if I write a Kirchhoff's voltage law equation around that right-hand loop, so during the transient condition, so for t greater than or equal to 0 plus, we would have VR plus VL plus VC is equal to 0. I can express all three of those voltage drops in terms of that current I. So that's going to look like R times I of t plus L times di by dt plus 1 over c times the integral from t naught to t I of t prime dt prime plus Vc at t naught is equal to 0. And once again, I can simply just take the derivative of both sides. And so that's going to give me L times the second derivative of my current plus R times the first derivative of my current plus 1 over c times my current is equal to 0, where the derivative of Vc at t naught is 0 because that's a constant term. I'm going to do what I did on Friday, and I'm going to divide both sides through by L so that the coefficient of my second derivative term is just 1. And so that's going to leave me with d squared I of t over dt plus R over L di by dt plus 1 over LC I of t is equal to 0. And once again, we are going to guess. In this case, we're going to say that we think I of t is of the form a e to the st. exact same guess value that we did for our parallel RLC circuits. And from this, we're gonna wind up having S squared AE to the ST plus R over L times S AE to the ST plus 1 over LC times AE to the ST is equal to 0. And now I'm gonna split things up again. So we're gonna have A times S squared plus R over L times S plus 1 over LC. All of that times E to the ST is equal to 0. And once again, we have a characteristic equation. That is a second order polynomial. So using the quadratic equation, we can say that S1 and S2 will be equal to negative R over L plus or minus the square root of R over L squared plus 1 over LC, all divided by 2, which if we move that factor of 2 from the denominator up into the numerator, you're right, thank you. Yeah, 4 over LC, thank you for that. Negative R over 2L plus or minus the square root of R over 2L squared plus 1 over root LC squared. And from this, we can see that for a series RLC circuit, alpha is simply R over 2L, and omega naught is 1 over the square root of LC. And from here, literally everything is exactly the same as if we had a parallel RLC circuit. So the only difference between a series RLC circuit and a parallel RLC circuit is that our definition of alpha is slightly different, okay, which is exactly what is given on our sheet. So actually, let me scroll up so you guys can see that while we talk about things here. All right, so we worked an example wherein we had a overdamped circuit with a parallel RLC system. So now let's work a series RLC circuit, but let's make sure that the system isn't overdamped, okay? So I'm just going to do a simple circuit here. Somebody hit me with a resistor value. All right, I'm going to change that to milliamps so that our voltages aren't ridiculous. Somebody hit me with another kilo ohm size resistor, please. 5K. Let's say, okay, so somebody hit me with a capacitor value. Doesn't particularly matter what it is. 10 microfarads. All right. And then over here, we're going to have an inductor, and we're going to sort out what value inductor we need in order to make sure that this isn't overdamped, just so that you have an example of something different. Okay, so we know that for the system to be overdamped, that means that alpha needs to be greater than omega naught, but we're trying to avoid that. So what we want is a situation where alpha is less than or equal to omega naught, because that is going to guarantee that we're going to have either a critically damped circuit if they're equal, or an underdamped circuit if alpha is less than omega naught. Either of which we haven't yet worked an example for, so we're just going to make this happen, all right? Alpha is R over 2L, and omega naught is 1 over the square root of LC. So we could say that R squared over 4L must be less than or equal to 1 over LC. We're trying to figure out what L is, which might be slightly problematic here, but we'll make it work. You are correct, and that will make things better. Thank you. Just making shitty algebraic mistakes here. Thank you for paying attention, Sebastian. So I think I can, and correct me if I'm wrong, I could say that 4L squared over R squared would have to be greater than or equal to LC, right? So if I flip my fractions over, I need to flip the direction of my inequality sign, if I'm remembering correctly. And I'm going to divide, let's see, so I can get rid of this L by getting rid of this squared. So L should be greater than or equal to R squared C over 4. R squared in this case, for what it's worth, is going to be 3 in parallel with 5, so that's 15 over 8. C was 10 micro. Divide that by 4. So our inductor looks like it needs to be greater than 8.789 henries. So let's make this guy 10 henries. Just to double check our work here, we're going to go ahead and calculate alpha and omega naught now, just to make sure that I didn't make any mistakes here. So alpha should be R over 2L. So that's going to be 15 over 8 kiloohms divided by 20 henries. Is 375 over 4, or 93.75 nepers per second. Omega naught is square root of 1 over LC. So that is the square root of 1 over 10 times 10 times 10 to the minus 6. Which comes out to be 100 radians per second. And yep, omega naught is greater than alpha, so this is indeed a not overdamped circuit. We would actually have an underdamped circuit in this case, right? While we're at it, omega D is going to be the square root of omega naught squared minus alpha squared. So square root of 100 squared minus 93.75 squared comes out to be 34.799 radians per second. Okay, so we knocked out step 4 first, just because I wanted to make sure that this example was going to be something new for us. All right, so now let's go back to step number 1. Analyze at t is equal to 0 minus, and let's actually go up here and explicitly specify what we're going to be interested in. So let's find our capacitor voltage. So that's something that we're actually interested in. Let's find the current flowing through this resistor. And we're not particularly solving for this, but we're going to need to pay attention to what's going on with our inductor current as well. Here's the voltage drop across our inductor. And actually, we're just going to call that current I. So these are all of the different pieces of information that we could possibly need here. So just to be clear, for our procedure, we need to know the voltage drop across the capacitor and the current flowing through the capacitor, the voltage drop across our inductor and the current flowing through our inductor. And then we're just going to use that information to solve for IR of t, however we can do so efficiently. Okay. All right, so analyzing the circuit at t is equal to 0 minus. So at t is equal to 0 minus, we have our current source, 3 milliamps. Our 3 kilo ohm resistor. Let's pull up here. Yep. Our switch is open. Here's our 5 kilo ohm resistor. Our capacitor is going to look like an open circuit. And our inductor is going to look like a short circuit. So here's the voltage drop across our capacitor. Here's the voltage drop across our inductor. Here's the current flowing through our system. So what can we easily say here? Okay, so I of 0 minus is 0 amps. I agree with that wholeheartedly. No current can flow through the open circuit. So VL of 0 is definitely 0 volts, because it's the voltage drop across the short circuit. VC of 0 I agree it's going to be 0 volts, but let's talk about explicitly why that is. Okay. So the voltage drop across our capacitor could also be expressed here as the voltage drop across this resistor, because the positive polarity terminals are both at this node and the negative polarity terminals are both at this node. Since there is no current flowing through the 5 kilo ohm resistor because it's not part of a closed current carrying loop, there's no voltage drop across it, and so therefore there cannot be a voltage drop across the capacitor either. Another way to justify it would be the capacitor isn't connected to any independent sources, so it shouldn't have any charge on it effectively. But either way we look at it, VC of 0 is 0. Okay, so I'm on board with that. Now let's analyze things at don't even need it, because it's not going to show up in any of our systems that we're going to write. So we're literally just going to figure out what's going on with the resistor at the very end. As long as we know what's going on with the capacitor and the inductor, we can figure out what's going on with literally any resistor just based on what's going on with our energy storage elements. All right, so at t is equal to 0 plus, our switch is closed. So we've got our 3 milliamp source. Here's our 3 kilo ohm resistor. Our 5 kilo ohm resistor. Our capacitor is going to look like a short circuit, and our inductor is actually going to look like an open circuit. So let me just write some things down here. So here's VC at 0 plus. Here's VL at 0 plus, and here's I at 0 plus. So we know that I at 0 plus has to equal I at 0 minus, so that's 0 amps. We also know that VC at 0 plus has to equal VC at 0 minus, so that's going to be 0 volts. The only thing that could possibly change would be our inductor voltage. So what do you guys think this is going to be? I disagree with that. How did you come up with that number?
So
Yeah. So I would do this using Ohm's law. So effectively, the voltage drop across our inductor is going to be the same thing as the voltage drop across the 3 kilo ohm and 5 kilo ohm resistors in parallel. So that's 15 over 8 kilo ohms times 3 milliamps is 45 over 8 volts by my mental calculations, which I believe wholeheartedly are correct. Yes. Okay. All right, so 45 over 8 volts. Anybody have any problem with our analysis here? Patrick?
what is EL 0 plus?
So in this case or in general?
Just like, I guess in this case.
So let's revisit a couple of things from circuits one, right? So in circuits one, we learned that the voltage drop across a capacitor cannot change abruptly, which means that VC at 0 plus has to be VC at 0 minus. We also learned that the current flowing through an inductor cannot change abruptly, which means IL at 0 plus must equal to IL at 0 minus. The voltage drop across an inductor can change as much as it wants to or needs to. The current flowing through a capacitor can change as much as it wants or needs to. So this isn't one of those quantities that has to stay the same. Okay. And then it's 45/8 here because of how the circuit is constructed. Yes. So because our inductor current is 0 amps, we need to replace it with a 0 amp source, which is the same thing as an open circuit. Because our capacitor voltage was 0 volts, we need to replace it with a 0 volt source, which is the same thing as a short circuit. So it is opposite of what we would be doing at DC steady state, but I want to remind you guys that at t is equal to 0 plus, we are not at DC steady state. We are at the beginning of our transient condition, right? So our system is in a state of flux. So in this case, it happened to look similar to like a DC steady state circuit, but it's all because the value of this was 0 amps and the value of this was 0 volts. All right, so now we analyze at t is equal to infinity. Okay, so at t is equal to infinity, now we are going to be at DC steady state. So let's see, we have our 3 milliamp current source here. Our 3 kilo ohm resistor here. Our switch is still closed. Our capacitor is going to look like an open circuit. And our inductor is going to look like a short. So let's see here. This is VC at infinity. VL at infinity, and IL at infinity. So let's start with the easiest thing. IL at infinity has to be what?
Well, zero.
Zero, yeah, definitely zero, because it's the current flowing in a not closed circuit. VL at infinity should be 0 volts because it's just the voltage drop across a short circuit. VC at infinity should be what? 45/8. All right. So we've done steps 1 through 4. So let's scroll back up to the top and let's develop a system of attacks for the things that we want explicitly here. Okay. So I know for sure that I want the capacitor voltage, and I also know for sure that I want the resistor current. The capacitor voltage is fairly easy. We can just set up a system of equations to solve for that. How are we going to solve for our resistor current? Okay, there's a couple of different ways that I can think of to do this. So actually, there are a couple of different ways, but there's only one way that makes any damn sense to me. So let's just talk about what that one entails. Okay. So in order for me to figure out the current flowing through that resistor, it's either going to involve the application of Kirchhoff's current law or Kirchhoff's voltage law based on other quantities that I can find, okay? So for example, let me do this in gray. I know that this current flowing in is 3 milliamps. And I know that this current flowing out of this node over here is just I of t. So realistically, I could do Kirchhoff's current law and find the current that's flowing through the parallel combination of the 3 kilo ohm resistor and the 5 kilo ohm resistor, and then use current division to sort that out. Another way that I could do it is I could add VC and add VL together, and that would give me the voltage drop across my resistors, and then I simply divide that voltage drop by the resistor value, okay? So which of those two ways seems like the smallest pain in the ass to you guys? The voltage way, okay. So that's going to require me to know VC of t, and it's also going to require me to know VL of t. Okay. So let's see. So VC of t is fairly straightforward. Okay, so we're going to solve for VC of t and we're going to solve for VL of t, and then we're going to add those two things together. So step 5. Solving for VC of t. Okay, so VC of t, this is an underdamped system. We figured that out at the beginning. So we know that generically, this will be of the form B1 cosine omega dt plus B2 sine omega dt e to the negative alpha t plus VC at infinity at t is equal to 0 plus. So what's cosine of omega dt going to be at t is equal to 0? What's the cosine of 0? 1. So we're going to have a B1 term. What's the sine of 0? So the B2 term is going to go away. Sorry, I need to put a bracket here. What's e to the 0? 1. So that bit right there is going to go to 1. So all that's going to survive the right-hand side of this equal sign at t is equal to 0 is B1 plus VC at infinity. And I don't know why my infinity signs look like garbage today. So putting in our numerical answers, that's going to look like 0 volts is equal to B1 plus 45 over 8 volts. So B1 must be negative 45 over 8 volts. So we know what one of our coefficients for our capacitor voltage is from the jump. That's useful. Now we could say that IC of t is C dV by dt. So that's going to be C times, and this is just coming straight from the table, omega d B2 minus alpha B1 cosine omega dt minus omega d B1 plus alpha B2 sine omega dt e to the negative alpha t at t is equal to 0 plus. The only part that's going to survive this is the C times omega d B2 minus alpha B1. Nope, because that's at 0, that just looks like a factor of 1. Yeah. All right, so, so let's substitute in numbers here. So IC at 0 plus. So I at 0 plus was 0 amps, so that's going to make things a little easy. So 0 amps is going to be equal to C. Actually, let's move this over here. 10 micro. Omega D was 34.7 something. 34.799. Alpha was 93.75. And then B1 was negative 45/8. And so we have enough information to solve for B2 just from this. Because I'm lazy, I'm going to use the numerical solver on my calculator. So I'm going to have 0 is equal to what I have stored in my calculator is A, which is that 34.799, but I don't want rounding error. Times X minus 93.75 times negative 45/8. Yes, that's 1. Solve for X. I get negative 15.154 and some change. And the units for this should be in volts. It's the coefficient of a capacitor voltage. So putting this together, we get negative 45/8 times the cosine of 34.799 T minus 15.154 sine of 34.799 T e to the negative 93.75 T minus 45/8 of a volt for our capacitor. We'll verify this with LT Spice probably at the beginning of our next class meetings. We've only got 5 minutes left. So how are we going to solve for the voltage drop across our inductor? Oh, because I wasn't paying attention. It should be positive 45/8, right? Yeah. And just as a double check kind of thing here, so we know that VC at 0 should have been 0. So this 45/8 and this 45/8 cancel each other out. So yeah, but thank you for that. Just making little dumb mistakes, and Sebastian's here to catch literally all of them. Good for him. All right. So the LFT, how are we going to figure that out? So the way I see it, we have 2 ways that we can do it. The first way is to set up a system of equations, just like we did here, using the inductor voltage and current, right? The other way to do things would be to take these coefficients that we got, B1 and B2, use them to find the capacitor current, because the capacitor current and the inductor current are the same thing, and then we just take the derivative of whatever that current that we get is. I am too lazy to do that. And what I mean by that is, to me, it's less work to literally set up a second system of equations using the table than it is to actually perform the calculus. So I'm going to set up the second system because all of the information is already provided to me. So we'll run through that really quickly, right? So just for sake of argument, so IL at T is going to be, let's call this B3 cosine omega dt plus B4 sine omega dt e to the negative alpha t plus I at infinity. I at 0 plus is going to look like B3 plus I at infinity. Well, I at 0 plus was 0, if I'm not mistaken. Put this down here. What was I at infinity? Also 0. So B3 is 0. So that's easy enough. Yeah, VL of T is going to be L di by dt, which is going to look like L times omega d B2, B4 minus alpha B3 cosine omega dt minus omega d B3 plus alpha B4 sine omega dt e to the negative alpha t. VL at 0 plus is going to look like just L times omega d B4 minus alpha B3. We know that the alpha B3 term is literally just 0, so I'm going to throw that away. So from that, the B4 is just going to be, VL at 0 plus divided by omega d times L. So that is 45/8 of a volt divided by 34.799 per second times 10 henries. (45/8) divided by times 10. I get 16.164 milliamps. So we're going to have L omega d B4 cosine omega dt minus L, sorry, I put a 4 there, not an L. Here. Alpha B4 sine omega dt, e to the minus alpha t. We ran out of time, so we'll finish this one up on Wednesday. All I did to get this part right here is literally look at this expression where I know that this alpha B3 term and this omega d B3 term are going to go away because B3 is 0. All right. So for what it's worth, at this point, you should be able to actually do all of homework set associated with parallel RLC circuits as well as series RLC circuits, because even though we didn't finish this one example, we're at the point where everything is the exact same thing as we've been doing. So what I would like to use Wednesday for, I can bring problems to work, or I could answer questions regarding your homeworks. My preference would be to answer questions regarding your homeworks because I think that's of more value to you. But I can just crank out problems all damn day too, if that's what you would prefer. So I'm saying that to say, I would suggest you start working on your homework problems now so that you can have time to ask me questions about them on Wednesday. All right. Thank you guys. See you later.